So, what's the connection between a nice, gentle breeze and a monster hurricane? Well, believe it or not, they're driven by the exact same invisible engine. And in this explainer, we're going to tear that engine down piece by piece and see how it all works. Okay, so here's the plan. We're going to start with the most fundamental building block, this unseen force called pressure. From there, we'll look at how air gets moving, how water gets involved, and then see what happens when it all comes together to create some of the most powerful weather on the planet. All right, first things first, let's talk about the force that really gets the whole show started, pressure. Now, you can't see it, and you don't really feel it like you feel the wind, but trust me, it's always there, setting the stage for everything that comes next. So what is this invisible force that's running our weather? It sounds like a really complicated question, right? But the answer is actually super simple and physical. It's just the weight of all the air stacked up above your head, pushing down. Yeah, that's right. The easiest way to wrap your head around this is to picture us all living at the bottom of a giant ocean, but an ocean made of air. And the weight of all that air pressing down on us, that's what we call atmospheric pressure. And check out how much that pressure changes the higher you go. It makes perfect sense, right? The higher up you are, the less air is sitting on top of you. I mean, look at these numbers. By the time you get to 10 kilometers up, where a jet flies, the pressure is just a fraction of what it is down here at sea level. It drops off super fast. Okay, so pressure on its own is, well, it's kind of boring. It's just weight. The real magic, the part where weather actually starts to happen, is when you get differences in that pressure from one place to another. That imbalance is what kicks the air into motion, and that motion is what we call wind. And this is the number one rule of weather, you guys. Air always wants to move from an area of high pressure to an area of low pressure. It's like water flowing downhill. It's a fundamental law. But it's not that simple because our atmosphere isn't just a straight ramp. Other forces jump in and start messing with that path. So it's really like a three-way tug of war that dictates where the wind goes. First, you've got the pressure gradient force. That's the initial shove from high to low. But right away, the Coriolis force, which is just a fancy name for an effect from the Earth's spin, starts yanking the wind sideways. And at the same time, friction from the ground is dragging on it, trying to slow it down. The wind we feel is just the result of this constant battle. Okay, so let's zoom out now. We've talked about the small scale, but these exact same forces are at play on a massive planetary level. And they're what create the huge predictable wind patterns that wrap around our entire globe. And this map here, this shows it all perfectly. You can see these giant blobs of high and low pressure that pretty much stay put. They're like the giant gears of the atmosphere. And the wind, well, it tries to go from the H's to the L's, but as you can see, the Earth's rotation twists everything into these incredible, massive swirls. This is the engine of our climate in one picture. So, to make sense of this whole global circulation thing, scientists break it down into three major loops, or cells, in each hemisphere. You got the Hadley, the Ferrel, and the polar cells. The main takeaway here is that together, they act like this giant conveyor belt, grabbing heat from the super hot equator and shipping it up towards the cold poles. Without this, the equator would be way hotter and the poles way, way colder. All right, so pressure differences make wind. That gets the air moving. But moving air is just, well, it's just wind. To get real weather, I'm talking clouds, rain, snow, you absolutely need the next key ingredient, and that's water. Now, when we're talking about water in the air, there are two terms you hear all the time: absolute and relative humidity. The sponge analogy is perfect here. Absolute humidity is just the total amount of water the sponge is holding, but relative humidity is the important one for weather. It tells you how full the sponge is. So 50% relative humidity means the sponge is half full. At 100%, it is completely soaked and can't hold another drop. So what happens when that atmospheric sponge is 100% full and then the air cools down? Well, cold air can't hold as much water as warm air. It's like the sponge shrinks. All that extra water has to go somewhere, right? It gets squeezed out, turning from an invisible gas, water vapor, into tiny liquid water droplets. That process is called condensation. And that, right there, is how you make a cloud. And it's wild when you think about it. This one single process, condensation, is behind so many things we see. That dew on the grass in the morning? Condensation. A thick bank of fog. Just a cloud on the ground, which is condensation. The frost on your car windshield? Yep, condensation.
And of course, every single cloud in the sky. It's all the same principle, just happening at different altitudes and temperatures. Okay, let's put some pieces together. We've got pressure making wind. We've got water vapor hanging out in that wind. Now, let's see what happens when you take huge, massive blobs of air, some cold and dry, some warm and wet, and you slam them into each other. This is where the real action begins.
First off, what's an air mass? Think of them as giant weather teams. You've got Team Arctic, which is going to be cold and dry, and then you've got Team Tropical Gulf, which is warm and totally loaded with moisture. Each air mass is basically a giant bubble of air that takes on the personality of wherever it was born. And when these different teams finally meet, the line where they collide is called a front. You should really think of it as the front line of a battle. This boundary is where almost all of the interesting, dynamic, and sometimes violent weather goes down. And the type of weather you get depends entirely on who's the aggressor in this battle. When a cold front is on the attack, that heavy, dense, cold air acts like a bulldozer, violently forcing the warm, light air to shoot straight up. Boom! That's how you get thunderstorms. But when a warm front is advancing, the warm air is lighter, so it just sort of gently slides up and over the cold air, which usually gives you that long, dreary, steady rain. So there you have it. That's the recipe. You take a big difference in pressure to get some strong winds going. You load that wind up with a ton of moisture, and then you smash different air masses together along a front. You put all that together, and you have the potential for some of the most violent storms on Earth. Now, when we talk about these huge, violent storms, they generally fall into two main categories. On one hand, you have extratropical cyclones. These are the huge, messy, sprawling storms that form along fronts, the kind that can cover half a continent. But on the other hand, you have tropical cyclones, you know them as hurricanes or typhoons. These are totally different. They're not born from fronts. They are pure heat engines, born over bathwater-warm tropical oceans, making them way more compact and brutally intense. And this image, wow. This gives you a peek inside the engine of a hurricane. All of its mind-boggling power comes from a simple process, condensation. As warm, moist air rises and condenses into these gigantic thunderclouds, it releases a staggering amount of heat energy. That's the fuel. This all happens in the eye wall, that ring of storms where you find the most destructive winds. And then, right in the middle of all that chaos, you get the famous eerily calm eye. So you see all this incredible, destructive power, and it's natural to ask, why? What is the purpose of all this chaos? And the answer is surprisingly elegant. It's all about balance. Our planet gets way more solar energy at the equator than it does at the poles. It's a massive energy imbalance. And these big storms, they are simply the atmosphere's most powerful and effective tool for moving that excess heat from the tropics to the poles to try and even things out. And maybe that's the best way to think about it. Is a hurricane pure chaos, or is it actually a form of order? To us on the ground, for sure, it feels like chaos. But from the perspective of the entire planet, it's a critical, necessary function. It's the Earth's climate system doing its job, fighting to find its balance.